Hi everyone! In this video we're going to talk about limits and continuity of functions of two variables. So if you think back to Calculus 1, we spent a lot of time in that course learning how to take limits of one variable functions, so functions of the form f of x. And here is the definition that we used. And so what this boils down to, and I'm going to draw a little picture here, is that our function, whatever it may look like, if this was a, then what we were looking for is, okay, as our function, as x approaches a from the left-hand side, it must approach, our function approaches this value L. And the same has to be true if x is approaching a from the right-hand side. Our function is still approaching this value of L. And if that was the case, then that meant that the limit as x approaches a of f of x would equal this value L. And so this is very similar to how we're going to find the limits of two variable functions. And one main difference is that since it's two variables, instead of seeing that x approaches a, we're seeing that a point xy is approaching some determined point that we're given in the problem of x naught, y naught. And so no matter what the path is, whether it be from the left, from the right, or now that we're working in two dimensions, whether it be a line or a curve that's getting us there, it always has to approach that same value of L. So let's go ahead and look at an example. So we have the limit of this function x squared minus 2xy plus y squared, all divided by x minus y. And we're looking as xy approaches 1, 1. And so thinking back to Calculus 1, the very first thing that we always tried with our limits was, can we do direct substitution? So if we do direct substitution here, we're plugging in a 1 for x and a 1 for y. So let's go ahead and try and see what we get. And so now I've substituted in 1 for x and 1 for y. If we evaluate the top and the bottom, well, the numerator, we end up getting 1 minus 2 plus 1. So we end up getting 0. And then our denominator is 1 minus 1, which is also 0. So here we have 0 over 0, which is undefined. And so in Calculus 1, after we tried direct substitution, and if this happened, we got an undefined expression of 0 over 0, then we would use other strategies. So we would consider, could we multiply by 1 using conjugates? Could we factor anything in our function? And then we also had like L'Hopital's rule. But in this case, we actually see that our numerator can be factored. And so let's go ahead and do that. And so you'll see that in our expression on the numerator, we have an x squared and a y squared term. So that means that our factors are going to need an x and they're both going to need a y, which is perfect because our middle term is an xy term and we have negative 2xy. So that tells me that our signs are going to be negative in our factors. And then we still have x minus y in the denominator. And then we see we can do some simplification here. We have an x minus y factor in the numerator and an x minus y in the denominator. And so those become 1. And then we have the limit as xy approaches 1, 1 of x minus y. And now we can do that direct substitution. So when we plug in a 1 for x and a 1 for y, we end up getting the value of 0, which is our limit of this function as xy goes to 1, 1. Now, this is to show that a limit does exist and finding that limit. But what if a limit does not exist, which we've seen this happen before in Calc 1 with one variable functions. But working with two variable functions becomes a little bit more complicated because, like I had said, for a limit to exist, no matter what path we take for xy to approach x naught, y naught, our function has to always have the limit of L or approach whatever that value may be. And so now that we have increased our dimensions, since we're no longer working with just a one variable function, but we have a two variable function, we have a lot more to consider than just the left and the right hand side. We now have to consider any curve that could pass through that point that we're given or that our xy is approaching. And so this is actually a little bit trickier to show because our limit could equal L or exist for several different paths. It just has to fail for one. And I'll show you what I mean by paths that we'll take that aren't just the left and the right hand sided. So let's look at this example. So we're asked to determine whether or not the limit exists. If the limit does exist, state the value of the limit. And so here we're taking the limit as xy approaches 0, 0 of the function x squared y squared all over x to the fourth power plus 3y to the fourth power. And so we could start exactly like we did with example 1. Can we do direct substitution? But unfortunately, if we do direct substitution, we would end up getting 0 over 0, which we know is undefined. And so therefore, we have to think of other strategies. So the strategy that may work is factoring, but actually in this case, our function is not factorable. And so let's just start by checking some paths that xy could travel to get 0, 0, or as it approaches 0, 0. And so first thing I'm going to do is a very simple one that we have been doing for our one variable functions, and that's going to be what if we travel along the x-axis? And so if we do, we need to consider how y behaves. So our y is always going to be on this x-axis, right? We're only considering taking this path. So in order for a point to be on the x-axis, that means that our y has to be 0. We can't move up or down at all from this x-axis. So we're going to set y equal to 0, and then we're going to take the limit as our x continues to approach 0, like we were told in our original problem. All right, so now we're going to rewrite this limit. We're taking it as x approaches 0, and now we're substituting in 0 for y in our function. So we still have x squared, but now times a 0 squared over x to the fourth power plus 3 times 0 to the fourth power. Well, our numerator simplifies to 0 because we have x squared times 0. And then our denominator, this term also is a 0, so it reduces to x to the fourth power. And again, we're taking this limit as x approaches 0. Well, we can already simplify this expression of 0 divided by x4, which is 0. So therefore, our limit along the x-axis is going to be 0 for our function. So now, no matter what other path, if the limit exists, it better be 0 for any other path that we take. So let's consider the line y equals x. So I'm going to continue drawing on this same graph. Oof. So if we have the line y equals x, it does approach 0, right? It crosses through the origin. And so that's why this is a path that we can take for this limit that we're trying to assess, because we're trying to approach 0, 0, which is done by y equals x. So let's go ahead and check this limit. So now, thinking about how our line is behaving with the x and the y variable, well, in this case, we could do the same thing. We could say that, okay, we're only going to focus on taking the limit as x approaches 0. But if that's the case, then what's happening to y? And we want to put y in terms of x because we're trying to get this to be a limit of a one variable function. So putting y in terms of x, well, that's y equals x. That's exactly what our line is. So, and we're going to let y equal x. And so now we're going to do the substitution and then evaluate our limit just like we did using the x-axis path. So we have the limit as x approaches 0 of x squared. And then remember, everywhere we saw y, we're now substituting that with an x in our original function. So we have an x squared times an x squared over x to the 4th power plus 3 times x to the 4th power. And so we're going to have to simplify. So again, we're still taking the limit as x approaches 0. X squared times x squared is x to the 4th power in our numerator. And then we have x to the 4th power plus 3x to the 4th power. So we have a total of 4x to the 4th power. We can still simplify. And if you see, we have an x fourth in our numerator, and then we have an x fourth in our denominator. And so those can cancel to be 1. So we end up taking the limit as x approaches 0 of 1/4, which is in fact 1/4. Remember the limit rules of constants. And so now we have the limit of our function as x and y is approaching 0, 0 on the line y equals x equals 1/4. But originally, when we considered the x-axis path, so that was when x was still approaching 0, but y equaled 0, we got 0. And so since 1/4 and 0 are not equal, or in other words, we got two different limits, the limit does not exist here. So to sum that up, since 0 does not equal 1/4, the limit does not exist. Now, I happen to find a discrepancy between the values of L, or the values of our limit, with just testing two paths. There is no set number of paths that you need to test before you can say, oh yeah, the limit does not exist, or oh yes, the limit does exist. You just have to test as many as you need. So like I said, in this case, we checked along the line y equals x and along the x-axis, but there's actually several different pathways. So for xy to approach 0, 0, you could have checked along the curve y equals x squared, or x equals y squared, or y equals x cubed, and so on. Any one variable function that passes through 0, 0 could have been checked as a pathway. So it's going to take a little bit of work to show and a little bit of creativity to choose those paths that you're testing. Also, I wanted to point out that once we did choose a path and we had a limit in one variable, we can solve using any of the Calc 1 tools and strategies that we had learned. So we could reduce, we could use direct substitution, we could use factoring, we could use multiplying by 1 using conjugates, we could use the L'Hopital rule. Any rule that you have used in the past works for two variable functions as well, once we've chosen a path though. And then also you can use the limit rules of the scalar multiple, the sum, the product, and the quotient rule of limits as well. So if you need to break up those limits, you can. All right, now the second part of this was talking about continuity. So we have 3 things that have to occur in order for a function of 2 variables to be continuous at a point x naught, y naught. And so that occurs if and only if f of x naught, y naught is second off, the limit as xy approaches this x naught, y naught of f of xy has to exist. And the limit as xy approaches that x naught, y naught of f of xy has to in fact be the value of f of x naught, y naught. So again, this is very similar to the definition of continuity that you had for one variable functions. Now we just have an x and a y to consider. And so if we wanted to think about this in terms of the examples we just talked about, well, number 1 says that first off, our function has to be defined at that specific point. And so if we look at example 1, when we use direct substitution in our function, well, we got 0 over 0, which was undefined at that point 1, 1. And so therefore, right away, condition 1 of continuity is not satisfied for this function. So therefore, this function is not continuous at the point 1, 1. There is a hole there. So I hope you find this video helpful, and I wish you luck as you evaluate your limits and determine continuity of functions of 2 variables.